So here we go. I'm going to do this one step by step using only things that we've already proven before, and then we'll package it into a new theorem called the Multiply Across Theorem. Yeah? So here we go. Suppose this is given. Again, I go back to my definition of fractions. This means 2 times 1 over 5. That's by definition of fractions. And this means 3 times 1 over 4. That's by definition of fractions. That's what the fractions means. Yeah, we've got no business in multiplying fractions if we don't have a good, solid understanding of what a fraction is. Or at least a powerful definition of it. Now I can rearrange things. I can say, you know what, I can do this 2 times 1 over 5 times 3. So I've moved the parentheses. This, of course, is associative law of multiplication. I can switch these things. I have 2 times 3 times 1 over 5. The inner items from the parentheses commuted, so that's called commutativity law of multiplication. Now I can reassociate again, and I can say, well, this is 2 times 3 times 1 over 5 times 1 over 4. And of course that's associative law of multiplication. And now look what I've done. Essentially what I've done is I've brought these things down and I've wrote the fractions that have 1's on top. Why? Because I already knew how to multiply the fractions that have 1's on top. For that we could use the multiply the bottoms theorem. This makes it incredibly nice and elegant here. This becomes 1 over 5 times 4. And now here I'm using the multiply the bottoms theorem, the one we just got done proving. And now I have something times something, 1 over something. This is the same thing as having something times 1 over something. And we said earlier you could use the definition of fraction backwards to write this as such. So we'll do exactly the same thing here. This is my square and this is my triangle. So this becomes 2 times 3 over 5 times 4 by definition of A over B. And there you go. We were able to glue the two fractions and show you how we multiply them. We multiply the tops and we multiply the bottoms. Step by step proof. It's beautiful. That word proof should sound so sweet in your mouth when you say it. Proof. True now, true in 1,000 years from now. It's so beautiful. The logic is irresistible. Of course, you could take one step further here and do a little times table. 6 over 20, and that would be by times table. And then you can simplify if you want, but that would be a different subject. Today, what I want to do is focus on the multiply across theorem. We're going to package these guys, all these steps. We're going to package into multiply the bottoms. Oh no, sorry. Multiply across theorem, MAT. Multiply across the top and across the bottom. That's why it's called MAT. Multiply across. Oh, it's so beautiful. Okay. Next time you have to do that, you don't have to reprove it every time. You can quote it. So this becomes -2 times -2 all over 3 times 4. I glue them together by multiply across theorem. And so now I can go with like this 4 over 12. And of course I could do by inspection now. By inspection means that we've already proven something many times. You already know how to do it. Here, just in case you don't, I'll show you. The top was by negative times negative theorem and the bottom was by times table. But these things, we focused on them the first couple of weeks of class. We can assume that you know them already, or if you're comfortable with them already, you can just say by inspection. It means I feel really comfortable with it. We've already proven it many times. These are really easy steps. There you go. Multiply across theorem. Okay? It works so well, it even works for things that we haven't even learned yet, like polynomials. It will work for all the fractions that you do for the rest of your life in any class, just about. So for polynomials it would go like this: -2 times x all over 3 times y squared. Y by MAT. Multiply across. I multiply the 2x, -2 times the x, multiply across the 3 times the y squared. That's it. Easy, right? Now, the multiply across theorem, interestingly enough, can also be used backwards. Backwards, to use it forward, you take the two fractions and you glue them together. Backwards would mean that you see them glued together and you unglue them together. So, take a look at this one. There's something famous called simplifying a fraction. And it goes like this. We'll do more of it next lecture, but today I can give you a little preview. I could say that the top is equal to 4 times 3, and I could say that the bottom is equal to 4 times 4. And I could tell you why this is justified. This is justified by the times table. 4 times 3 is 12, 4 times 4 is 16. Now you can look at this and say, whoa, it looks like somebody glued my fractions together, glued these fractions. Maybe, by using MAT, maybe we can unmat them. That would be 4 over 4 times 3 over 4. That's by multiplying across theorem used backwards. If I was to multiply across, I would get to the previous step. Multiply the top and multiply the bottom. This is ungluing them. Same reasoning, MAT, from right to left. Now this piece right here we can clean up. 4 over 4 we did last time. We proved that that's equal to just 1 by the just 1 theorem. And of course 1 times anything would be that same thing by the multiplicative identity. And so this would be a very, very methodical way, professional way to simplify fractions. And at the heart of it is this multiply across theorem where you unmultiply them. Right here, this is the heart of it, splitting this up so that you can kill that 1. Okay, very nice stuff.